Okay, welcome everybody to this Halmstad Colloquium, one of a series of talks where invited speakers tell us about an exciting current field of research. Our speaker today is Professor Marco Mugnaini from the University of Siena, and Professor Mugnaini has a very impressive publication list covering some very interesting sensor applications and Internet of Things applications. But today he's going to be talking about his work on reliability prediction with software, so using computers to try and predict how things are going to go wrong, might be the best way of saying it. So thank you, welcome, lovely to have you here, and we look forward to your talk.
Thank you very much for the kind introduction. Okay, thank you for being here. My name is Marco Mugnaini, and I work as associate professor at the University of Siena, and I'm also IEEE Instrumentation and Measurement Distinguished Lecturer. So that's the reason why of this template here. The title is general because it's linked to dependability subject, which means everything that is connected to fault detection, fault prevention, fault management, and reliability, availability, and design for safety. So that's the reason why of this title. Moreover, the focus will be on some examples linked to industrial applications. Definitions. Most of you is well aware of what reliability is, but this is just a small recap. Reliability is the ability of an item to perform a required function, which from now on I will call mission because it's one of the most important things in defining reliability assessment, under a given condition for a given time interval. But this is not really exploitable definition in terms of engineering. Why? Because it's the ability cannot be measured. So this kind of concept translates to a probability. As a matter of fact, in terms of things that can be exploited to make evaluations. The same concept applies also to availability, which is barely similar to reliability concept, but here we introduce the argumentation that time can be interrupted. So it means that basically you have to keep into account maintenance actions. So you're not interested in the time to failure of an item, but the mean time to failure, that is how much is going to be usable, okay, over its life. And then safety, where the objective is to free your item from unacceptable risk of physical injury to persons, okay, basically. So, why reliability and dependability is important? The reason is because there is a wide bunch of examples where reliability matter played a role. For example, here I reported here just 3 events that are in the mind of persons, I suppose. One is the Challenger event, which costed the life of the entire crew of the shuttle. And this is due to the failure of a basic 70 sensor ring. And the Deepwater Horizon out of the Mexican coast, where a valve placed in the bottom of the ocean failed, and this caused this huge event with a lot of consequences in terms of environmental impact. And here there is simply a collision between a tree rail with a garbage truck that happened on January the 4th, 2016, with small consequences. But this is just to provide you an overview that reliability and safety is not just linked to electronics or computer science. It's something that affects everything in our life, because whenever you design a card, an electronic board is to perform some kind of actions or to interact with a mechanical system or with other electronic components that at the end of the story will have an actuation system. So the problem is that to perform reliability study, you cannot just segmentate your knowledge in terms of electronics or mechanics or chemistry. You have to see the whole picture, okay? So this is how, in my mind, this is the acronym of reliability, availability, maintainability, and safety. So it's RAMS. works, okay, according to me. Reliability, of course, is concerns both hardware and software, but on this kind of presentation, I just focus on hardware problems because it's too wide to be discussed in a single session. Where we start from? Usually we start from field data, that we get information from the field, what happened into the field. We look at the physics of items, looking for failure modes, why things fails. We go together with statistics, because when you get field data, you have to analyze them in a statistical way, because usually if you have the failure mode of a single item, it doesn't make you any kind of experience to treat that item as a whole bunch of similar items. And then together, joining together these three sectors, you can get the reliability information on a specific item. Then if you add maintenance concept, as I was telling you before, you can get the availability concept, and if you add consequences to availability, then you can get safety analysis. Of course, maintenance has also a maintainability branch that goes by itself, where you are planning maintenance in order to optimize the exploitability of items or components, okay? Where we start from? This is the basic rule, and this is the usually the discrete representation of reliability. And here I reported just what are the most important things in terms of theoretical approach. You need a reliability definition, which is just the ratio between the working items at a certain time over the overall bunch of items that you are testing. The unreliability, which is just the cumulative distribution function, which is the number of failed items over the overall number of items that you are testing. And of course, the number of working items plus the numbers of failed items is always equal to n, which is the overall number of items. So 1, the reliability, is always a decreasing function, or not increasing, and the unreliability is just a non-decreasing function that is always usually increases. And this function here, which is called the hazard function, or it's well known as failure rate when it's constant, is the key part that allows us to perform reliability, availability, and safety study. Safety needs some kind of further definition, but we will see later. Together, combined, if you want to get an analytical expression of reliability of almost every item, we get the fundamental reliability law, which tells us that reliability over time is always an exponential decreasing function, where we have to integrate the behavior of the hazard function over time. So, summing up, if you are able to know the hazard function of an item, we can evaluate at any time its reliability. Okay? This is something that is found into the literature, and this links to the previous slide that I've shown before. That is, we need statistics. Why? Because to model the hazard functions, usually we can, or basically the behavior of an item, we need to collect information from the field and to see if some of the well-known uniform, Gaussian, log-normal, gamma, exponential, Rayleigh, Poisson, or other probability density function fit the behavior of our item. The most used probability density function in reliability is Weibull. Why? Because it has a nice shape. If we look at this diagram, here there is the representation of the failure rate with respect to time. So it means that usually what happens is that there is a first phase where items are placed in the market and they're new, so you get a high number of failures that is going to decrease over time. Then you get a steady state, which is called also random failure mode area, and then you will see that failure rate is going to increase over time due to wear out. Okay, this is called bathtube curve. But of course, not the item has the same shape. That is, the idea is the same for everyone. We will come later that not always is like that. But as a matter of fact, what you find in the literature is this one, okay? And for electronics components, basically the most important part is the random failure rate, where you treat the failure rate as a constant number. So the previously seen formula becomes constant, not a function, while for mechanical components we have this one which is most important. So the wear out is important. What happens is that if you start from the probability density function and you define the hazard function as the ratio between the probability density function and its reliability, and you get the reliability as the integral of this probability density function, you will get that the Weibull probability density function allows you, depending on the failure, on the values of the shape factor and on the characteristic life, to model each branch of this kind of curve. So with a single probability density function, you can basically cover all the conditions, because, for example, if beta is less than 1, this is the inverse of the time, so it's a decreasing function. If beta is equal to 1, it's constant, so the failure rate is equal to 1 over eta. If instead beta is greater than 1, which happens for all the mechanical components, then this is an increasing function. So you can use just a single probability density function to cover electronics, mechanical, electromechanical components, and everything that pop-ups in your mind. So here, what happens to our reliability fundamental law? Do you remember it was an exponential where we integrate the hazard function? Well, if you are dealing with an electronic component where you have that the hazard function is a constant, which is called failure rate, then this becomes just a simply exponential decreasing function. But is it something that is manageable for to be delivered to customer? And is it something that can be made valuable for persons that are not engineers? No, not really. You cannot go to a car seller saying how much reliable is this car, and is going to provide you, yes, a number like it's a 0.998 reliable in a certain amount of time. It's something that you cannot touch. And for this reason, there are some kind of synthesis indicators that are called mean time to first failure for not repairable systems, or mean time between failures that is used for repairable system that is usually provided. And the definition is quite easy because it's just the mean of a random variable. So that's where it comes from. So it's the integral of the reliability from 0 to infinity, not from minus infinity, because time is always a random variable which goes from 0 on. No, you cannot come back in time. But is it good? The answer is no. By itself, no. It's not good because it's an average. So in an average, it depends on the sample amount and what is the variance or standard deviation, because the average by itself is not meaningful. No. So the point is that how can we analyze reliability in terms of an analytical description of my situation and then place numbers in order to perform a forecast? I'm talking about reliability, but this works also for availability, of course, and safety. Usually we start from a system that has to be modeled. We build a reliability block diagram, which means a collection of items, because we analyze the system from a bottom-up approach. That is, we start from a single items and then we arrive collecting them to the whole item, and then we perform the reliability estimation. But in making this reliability block diagram, we can face different configuration, depend on the complexity of our system. We can get canonical configuration, which can be easily treated in an analytical way, so you can get a closed form solution of the system. And these are series, parallels, hot and cold standby. This is our most common configuration that we find in aircrafts or in electronics stuff, or in other kind of everyday used device. Or you can get mixed configuration. Again, they can be solved in closed form solutions, and again, this can be found in oil and gas and refinery plants. Or you can get non-canonical solutions. So this is due to the fact that there is a huge amount of components, and therefore it's heavy to get an analytical solution, and therefore to get some kind of information on reliability of this kind of configuration, you need to perform usually Monte Carlo simulation. So everything is based on simulations. These are the most widely used reliability technique for assessment and ex post evaluation. And these are divided into three huge families. The first one is quantitative methods. So it means that these are methods that can provide you with numbers. At the end of the story, you are interested how much is the reliability at a certain time, and using this kind of methods, you can have an idea. But of course with a certain bound and boundaries, confidence bounds. Qualitative methods just provide you a kick-off analysis tools for reliability investigation, but you don't have at the very end of the story sharp picture of how much is the reliability of your item. You have just an idea. And then you have semi-quantitative methods that are used to evaluate easily what happens to your system without a huge analysis. And some of them are taken directly from the logic of computer, like the first one, which is called fault tree analysis, and is based on logic combination of input-output. Okay, you start from basic events, and what happens is you combine them with logic ports like AND, OR, XOR, a lot of them, to get the final event. That's called the top event that you want usually to avoid. So you can even think to approach this kind of analysis in terms of unreliability analysis. Okay, but the key point is that, okay, I have to place numbers here. No? Instead of that xi, I need the probability. And this probability is the evaluation of a certain failure rate at a certain time following what? The reliability fundamental law. How can I place number there? In electronics, this is a tough task. Why? For example, if the required failure rate of your item is 100 failure units, which means that this is a measurement of time, because usually it means that you expect to have the failure rates are given as a number of failures over million hours or over billion hours. It means that if you want to get an idea of the time required to observe one failure in 100 devices, it takes around 11 years. So you start today, and in between 11 years, when your component is completely out of date, so no one is going to use it, you will have an idea of how much will be the failure rate. So this is now the process, of course, and that's the reason why accelerated testing has been introduced not only in electronics but also in mechanical and in structural engineering. What are the four common stresses used for performing accelerated testing? One is temperature and voltage, current. These are more related to electronic components. And temperature cycling to accelerate mechanical failure of chips and assembly package. This is linked to computer science, of course. We can find even accelerating factor for mechanics, which is cycling, and fatigue cycling, which is linked to mechanics and structural approach. There is a point here. Usually, you would like to accelerate items just with one acceleration factor. But what happens in the lab is that maybe you are accelerating with, you are just applying one of these, but more than one is going to happen together. So the point is that at the end of the story, am I sure that my acceleration is due just to one single item and not just to the combination of them? That is, the information that I get is just linked to a single acceleration factor, or is a combination? Because otherwise, the number that you are going to figure out of your experiment and you think is linked to this acceleration factor cannot be used and not be exploited as the failure mode or the failure rate, of this component. What are the most known acceleration laws? Arrhenius, which is a first order, let's say it's used in chemistry, it's a first order law reaction. And this is used just in semiconductors to accelerate components with respect usually to temperature. So you get an information on how much is the activation energy and therefore a failure rate of a component performing experiment at different temperature on the same kind of item. But if you need to combine more than one acceleration factor, that is, I want to get information on what happens to my component if it's in a heavily changing temperature environment and in a, let's say, humid environment, then I cannot use by itself just the Arrhenius formula. I have to use a more complicated equation that is called IRING, okay? And this is an example on how the probability density function exploiting the Arrhenius equation comes from, and that's the expression of reliability. And these factors here, A, B, and V, has to be evaluated time by time on every kind of component in order to assess how much is the failure rate. But do we have to do that really? The answer is no, unless you design your own device starting from the silicon, okay? Otherwise, as an alternative, there is someone who has done already the job for us. That is, you want to look at some components that you want to use to perform your reliability investigation because you are designing a new board or you want to evaluate the reliability of a board designed by someone else. Then you can rely on several kind of databases that are available. The most used and the most recognized and the eldest, of course, is this one, is the Military Handbook 217. Here it's the F version reported. This is a database developed by the Department of Defense of the United States and has a wide collection of items in there. This is the database that is mostly used by all the organization that requires for reliability assessment. That is, you design your own new sensor, design your own new electronic or electromechanical device, and you want to deploy that to the market. If the customer wants a reliability analysis, usually is going to ask you, can you please perform a reliability analysis according to this standard? Because this standard is more conservative generally than the other. Of course, it's limited because it's not updated and it has no all the components inside, but it's a good starting point. Which are the factors that affect the semiconductor or in general component failure modes and failure rates? Before, I've told you that there are qualitative or semi-quantitative reliability techniques. Why are these used? Not to get a number, because these are qualitative, no? But it's to understand which are the most important failure modes connected to my mission. And here we come at the very beginning of my talk. The mission is most important. Think to this mobile. If you don't define the mission, it doesn't make any sense to ask for reliability assessment, because you can think that the reliability is connected to the actual use that anyone that has a sense can do of this mobile, or simply you can give this to a child and for him he can use this as a hammer. So the reliability of this mobile is not the one that everyone is intended. It depends on the mission, that is the use that you want to have of this kind of device. So the same thing happens here in a more generalized way to all the components. What is important is to define the mission. So once you have defined the mission, what are the failure modes that are most important? It depends on the application field. For semiconductors, for example, we know that printed circuit boards are vulnerable to environmental influences because they are corrosion prone, they can be improperly etched, and there can be some impurities into the manufacturing, and there can be also soldering problems, okay? So problems that are not evident at the beginning can become evident during usage, shortening the life of your item. Of course, there can be different kind of failure modes that can be linked either to the mechanical assembly of the electronics that you are using, or can be linked to the chemistry. And for example, you can have also soldering flux, which may residues, which may facilitate corrosion, or polar covalent compounds, which can attract moisture like antistatic agents, and then you can have ESD discharges on your components. Okay. The most known failure modes for that worked for aluminum at the beginning of 80s was electromigration. Maybe you know that one, where if you have lanes that are subject to constant current, you have a transportation, mass transportation of material, and due to the high current density, what happens is that you have a transportation of material which enhances the current density due to the limited amounts of material that lays in a single spot. So what happens is that if current flows here, this is also for platinum, at a certain moment material transportation takes away material from a specific point, enhancing here the current density, and so it's an avalanche effect, and at a certain moment you will not get this kind of failure mode at the beginning of testing, so it's a hidden failure mode, but you will discover overusage. No? Other kind of failure modes that are usually frequent in electronics are ESD, so you get electrical discharge where thousands of volts are localized in a single point, burning up during assembly your chip. And of course, for example, for metal oxide semiconductors, other failure modes that are important is accumulation of charge carriers in the gate oxide, because this changes the transition threshold voltage. And this is something that affects also the reduction of dimension in electronics, because if you reduce a lot dimension, then the threshold is going to get lower for transition because dimension is very, very low. So this is also a reliability problem that is connected to miniaturization of circuits nowadays. Summing up for semiconductors, we have to keep in mind that these are the most important points affecting semiconductor reliability. They are very sensitive to impurities and particles. There are problems in microprocessing of thin films because if you don't understand them fully, then you can have problems even in the metallization, in the assembling of the SiP. So you can think you have designed everything properly. When you make it and you deliver to the market, then you can have something that is coming back to you soon, which is not expected. And of course, the environmental conditions plays a role, because the stress factors affecting device reliability may be found in the assembly environment. Okay, it's not just the design; it's the fabrication process that is a problem in semiconductor. Which are the most important failure modes in mechanical system? In mechanical system, you have fracture, and you can have fatigue, and you can have creep. Okay. And these are important because, for example, for aircraft industries, this is one of the most important things that have to be investigated. Of course, this is an example where the cycle with respect to life is described, and it follows the Basquian equation, where you have that sigma is the stress amplitude and P and C are empirical constant. And what happens here is that depending on the kind of material, you can change the material trying to enhance its strength to number of cycles, because the fatigue life is follows an inverse proportional law with respect to grain diameter. So it's not just the way you use the item, but also how you implement the item. How do you get your metal? This is always happen also in chemical sensors. If you consider, for example, metal oxide sensors, and you consider, which are gas sensors, and you consider the most widely used gas sensor, which are tin dioxide gas sensors. These have been widely studied since a long time. Tin dioxide surface actually doesn't mean anything in terms of reliability, because having the same material doesn't mean that the same sensor with the same layer has the same reliability, because it depends on the fabrication process. Okay? How do we pass from reliability to maintenance? To availability. Adding maintenance. Again, is there a figure that can be used to make this kind of concept widely popular and accessible to persons? Yes. Usually, if you work with items, a figure that is always required is the steady state availability, which is this number here, which is always the ratio between the mean time between failure and the mean time between failure plus the mean time to repair. As an absurd, think that your item is going to break every second, but if you repair every nanosecond, basically is always available. Okay? Instead, you can have an item that never breaks, but when it breaks, it needs a lot of time to get restored, then its availability will be pretty low, because this number counts here. Okay, so this is again a number that has to deal with probability, because it's a number bounded between 0 and 1. 1, it means it's always available, and 0, it means it's never available. But how do we model the availability of every kind of item? Usually we use this kind of approach, which is called Markov chain. This is a memoryless chain, first order homogeneous chain, and it's also used, this kind of approach, in telecommunication to describe transition properties of information. Usually you have a certain number of states describing the system that is working, and a certain number of states that describe that the system is not working. And here what you want to know is how much is my probability to get a transition from a working state to a not working state, a non-working state. This kind of system are usually designed for electronic equipment. Why? Because here this probability is the product of an infinite time measurement, an infinitesimal time measurement, and the constant failure rate. But we have seen before that constant failure rate is used for electronics equipment. And this kind of approach provides the possibility to get an analytical solution to this kind of problem. So what we get is that the availability can be described as reliability in an analytical way almost for all the electronic components, which is not for mechanical, which is more difficult, because instead of having a constant, you have a function. What is the role of maintenance? Maintenance is important because this is just a sum up of the most used maintenance policies in general for electronics, mechanics. You have corrective when the event happens. You have improving if you have to increase the performance. You have opportunistic to optimize downtimes, and you have preventive to prevent forces outage. But does this kind of maintenance can be applied to all the components? And the answer is no. For example, if you want to use preventive maintenance for electronic components, purely electronic components like PC, that's a nonsense. And this makes even things worse. It can be proven, no? You can build up a reliability function, and at the end of the story, applying a preventive approach just to evaluate if things are getting better or not. If you get an advantage in performing preventive maintenance, you just make the ratio between the original reliability and the reliability of your maintained item. If this number gets higher than 1, it means that you don't have any kind of advantage. If it's lower than 1, yes, because it means that the reliability of the maintained item is higher with respect to the reliability of the original item. But here, if you take a purely exponential item, which works for any electronic component, as we said before, the outcome is 1. 1 in the best conditions, because otherwise you have to take into consideration that any time you perform preventive maintenance or any maintenance activity, you can fail. So reducing the reliability of the original item. So generally, this number for electronic components is lower than 1. So it's better not to touch your PC if things are going on, okay? In a right way, in a proper way. Instead, for mechanical component, it can be proven that using the Weibull representation that we have seen before, that this ratio is greater than 1 if and only if beta, which is the shape factor, is greater than 1. What does it mean? That the component has to be mechanical. That's the reason why you bring your car to the service shop every certain amount of kilometer or a certain amount of time. Because mechanical components are following in the Bethune curve that we have seen in the beginning, the last part, which is due to wear out. So the failure rate or the hazard function is always increasing with time, while for electronic components is always constant. It's in the random area, so it doesn't make any sense to perform preventive maintenance. You are not going to change or affect the reliability performance. How nowadays we hear a lot of big data, how big data can affect reliability analysis. Oh, they can be used to describe, to get some kind of surrogate indicator, and one of the possible application is process raw acoustic emission. This is mostly used for mechanical guys, and this can be used to extract feature to predict fatigue damage. And to do that, you need to pass through the entropy concept, okay? Why? Because in mechanical, the dissipation of energy is linked to damage, okay? And this is linked to entropy generation. So if you're able to link the dissipation of energies to entropy generation, then you can understand the degradation mechanism and you can prevent damage. And this can be done through a lot of data processing and data gathering from the field. Okay? And this is just to sum up some kind of general concept. First one is that failure occurs when the accumulated total entropy exceeds the entropic endurance of the unit. That is, you set the threshold for your item in terms of entropy. If the information you get from the field from sensor exceeds this threshold, it means that your system is going to undergo to soon damage. Okay? And entropic endurance of identical units is equal. Entropic endurance of different unit is different, and that's important to discriminate between different items in the field when you get information from the field. And entropic endurance to failure can be measured, okay, and involves stochastic variability. That's a consequence. That's how it was done reliability assessment for mechanical system into the past. You get historical failure data information, but you didn't perform any kind of model, and you try to model physical damage model, and you try just to fit some kind of probability distribution, density function on the failure that you get from the field. Nowadays, what we do is you perform you try to understand which is the failure mode, first of all, if it has been fretting, corrosion, fatigue, wear, and so on. Then you try to understand the physical damages, if it's due to one of these or a combination of these, and then you try to link the damage to the time to failure. What is done with big data is that you understand the dissipation process, if it is a mechanical losses, heat conduction, diffusion losses, and so on. You try to map this kind of dissipation process into an entropy and to link the entropy to the time to failure. Okay? This is an example for acoustic emission signals. You get the signal, you perform the spectral analysis, and then you count simply how much this histogram is above a certain threshold, and determining if this number of counts stays up to a certain threshold for more than a certain allowed period, then you get your information on the damage and on the failure. But is it everything so easy? The answer is no. Do you remember the bath tube curve that I've shown at the beginning? That was, okay, in the literature you will find this nice curve for components, okay? This is the failure rate over time of a LNG plant. LNG plant stands for liquefied natural gas plant, okay? So it's an actual plant. Do you see that this is going down as expected in the bath tube curve? So you should see something that is constant, or at least, okay, if it's not constant, it's increasing, but then it decreases again. So it's nonlinear function. What's up? This is actual life. When you put together lots of components in a plant, this kind of curve doesn't apply really. Why? Because you are not dealing with just components. We are dealing with humans. What happens here? Here happens that maybe there is a commissioning phase at the beginning where you try to reduce the number of failure because it's the seller who owns the plant. At a certain moment, there is a change, a shift change. That is, the seller provides the key to the customer, and the customer has his own crew that is getting on the plant, and he discovers a lot of things that the others just fixed to deliver the plant. So this is actual life, and the point is that we have to change our curve. That is, we want to fit this curve because this is what we want to predict. We cannot say, okay, they made a mistake in data collection, okay? So the point is that we have to think to other kind of reliability statistics. We have always to follow the reliability fundamental law, but what we have to do is that we have to try to describe our law in a more complex way, exploiting more information on Weibull multi-parameter function. If you follow the constraints of this kind of statistics, you will find, I will skip this math, this is just math that tells you that we are dealing with the probability density function. So they have exactly the same constraints of all the probability density functions. And at the end of the story, you can find that these constraints have to be physically acceptable. That is, you have to be able to model that in a certain way. What you get at the end is that you can find this kind of parameter for this specific case, and you can find, a curve that fits at the best this kind of numbers, okay? Of course, you will never find a curve that is fitting all the points because they are scattered here in an unreasonable way. But that's what you get from the field, and that's what should engineering do. That is, try to find the best model, the best approximation that helps you to solve this kind of problem in an analytical way, or at least to perform simulation. And this is how the reliability of this component behaves over time. So, starting from something that was not modeled at the beginning or could not be modeled, at the end of the story, you finish up with the reliability function. So you have an analytical description. These are other examples on that are true, and these are continuous date, okay? These are similar of what we have seen before. As an alternative, you can even try to approximate this kind of curves with piecewise linear curves. Of course, what's the problem is that you will never get an analytical solution because it's a nonlinear function even in this case, okay? From reliability to safety, I'll try to move as quick as I can. To once you get a picture of the reliability and of the availability of your system, and you want to analyze the safety part, then you have to rely on this standard. This standard is the IEC 61508, and is a general purpose standard for electrical, electronic, and programmable electronic equipment. And these are all the standards that are derived, and maybe you know them, and this is part of this standard here. So if you're able to understand these standards, these are quite easy, okay, for you. What's the difference from reliability? In reliability, there was the failure rate, and that was the only thing that was of interest for you. In safety, then it depends on this failure rate, where it comes from. That is, what are the failure modes that are important for the safety of your item? So you have to start splitting them into two halves. The failure rates that are safe, which I really don't care too much, and the failure rates which are dangerous. But at this point, I have to ask myself, can I see all the dangerous failure rates? And the answer is again no. You can have dangerous detectable failure rates, failures, so failure modes, which provides you a certain failure rate, so that's the better description. Or can I have some kind of failures which provides you a part or a fraction of the overall failure rates which can be undetected, and this is the most hard part, okay? Usually in this standard there is a thing that is called the safe failure fraction, which is just the sum of everything that can be detected and safe over the overall item. That provides you a quantitative idea of what's safe and what's not. These are the tables that I've told you before, and concerning the safety, because here usually we divide the safety level into 4 levels, 5. SIL 0, SIL stands for safety integrity level. 0, it means no safety concern. 1, 2, 3, 4. The lowest here means the lowest is my effort in providing a safety function to my system. The highest here means that I have to work a lot to make my function as safe as possible, because I have to cover a huge gap for safety. And this is the probability of failure on demand that I require to cover for on-demand mode applications. This table here, I reported here, is of interest because in the standard you have to discriminate between well-proven items and new items. That's something that happens also in space applications. No? In space application, you don't use the very last PC or computer that you have in the market here. Why? Because you cannot admit any failure once you are outside the orbit. So the point is that it's preferable to use well-known technology, even old technology, where I am quite sure that all the failure modes have been investigated and the working condition of my item are well known, well defined. So here, for example, in the standard, it's defined, the items are divided in 2 classes, type A and type B. What does type A and type B means? Type A means well-known items. Type B means new items. Let's suppose tomorrow you develop your own sensor, new sensor, and you want to use this kind of sensor for safety application, and you want to cover a SIL level of 3, for example, and you don't have a safe failure fraction, and you have a safe failure fraction which is less than 60%, you can never use type B component to get this level, because simply the uncertainty is too high. You cannot do that. So forget it. Even if you perform any kind of let's say redesign of the system, simply what is missing is the knowledge on all the possible failure modes of your item, which takes time. Another parameter that is important is diagnostic coverage, and it's defined as this part here, okay? Because the diagnostic coverage usually is considered high when it's above 99%, and this is you see, it seems challenging it seems that these are challenging numbers, and instead, if you are less than 60%, it means that you basically you don't have any kind of diagnostic coverage. But why these parameters are important? Because whenever you define a safety function has to be thought to something which is apart from a control function. Think to a plant, a power plant. This kind of standards applies to all the functions which are not designed for the normal working of the plant. But these are functions that have to take place just when they are needed, maybe once in the plant life. But the point is that when they are needed, they have to work. It's like driving your car, you push the brake, maybe you push it just once in the highway, but when you push, you want the car to get slower and to stop, hopefully. You don't want to say, okay, this function is not working, never used, it was in my car, and then I get crash. No, so here the function is always can be defined through several components. One is sensor, the other one is logic solver, and the other one is failure and is the final element. And this is important because you don't have to think that safety is just something for electronic components, for computers, for sensors. It's something that has always to be interfaced with a physical actuated system that usually is a mechanical component. So you cannot say I'm studying the safety function of an electronic system. It doesn't make any sense. You are ending here, which can be the safest part in the world, the safest function in the world, and then you are interfacing with a really poorly safe mechanical item, electromechanical item, and nothing will work. So you have to see the whole picture. This is an example of, it's taken from the standard of how the safety level, integrity level will change according to the kind of redundancy. For example, you can get a safety integrity level 1 if you have a single chain. You can increase to 2 if you have a multiple chain, and if you have a voting system, you have even get a higher degree of safety. Okay, how do we study that? Again, another tool can be Markov approach. Markov chains. That's the reason why it's important to start from reliability. If you start from reliability, it's like collecting bricks of a house, no? You start from reliability, you get an idea of what your item is. Then you add maintenance and you get an availability idea of what your item is. Adding maintenance and dividing the failure rates into several parts, you can get further information concerning safety, okay? The approach is exactly the same, okay? Problem. This is an example, no, of practical companies. You have to understand the incident at level crossing, no? And there are different level crossing size, shapes, so you have to understand, okay, what is the best sensor that I can use here? The best sensor that I can use, sorry, I'm coming back. The best sensor that I can use depends on the shape of my level crossing, okay? But is this something that I can define in advance? Yes, you have to consider both hardware and software, but also communication and sensor physics, which is not described into the standard, is important. What are the solutions? Sorry. Solutions that can be used to detect if there is something in the barrier of a rail passage. The most used are optical solution, which are laser sensor, inductive solution, or it can be just radar solution. These are the most widely used techniques. Which are the advantages? Optical solution, it's efficient, but performance is linked to operating condition. If there is fog, you will never see anything. Buried solution, that is inductive solution, is simple and cheap, but it's really linked to the area, so it's not general. And then you have radar, which is good enough, but it's more expensive and the tuning is hard. So which one you want to use? We have proven all of them, but we have selected the radar one, which is the most promising. This is a basic configuration where you have, for example, a radar and you have its reference object on the opposite condition. This is the radar that we have used, or it has been used as a frequency modulated waving radar. And this is the reliability study, where we see that we have tried to understand how much the reliability could be enhanced changing the sensing, just the sensing condition. And this is the general framework where we have to move. That is, we have to divide the hardware and software from the signaling and the communication. So it's speeding up, but the point is that if we follow this roadmap, which is basically composed of all the squares are the what we have seen before. Sorry, I'm getting out, which is better, so it's going to get steady. These are exactly the path that I described before in synthesis, called with different name, but basically you perform the reliability analysis, the availability analysis, the safety assessment following the standard. At the end of the story you get with numbers. Is this enough? Because you are following the standard. Can you say that your system is safe? The answer is no. Why? It's easy because physics of the sensor plays a role here, and physics is not considering to the standard straight. It tells you you have to know your system, but sometimes it may happen that you don't know everything about your item, your sensor. And here, for example, there is a misdetection probability that you have to evaluate. Sometimes when you use a radar, you're not sure that you are detecting the item. It's in the physics of the item. It depends on many factors. But even if you consider, are you done? Does it work? Have you finished? And the answer is no again. Because let's consider you place a radar here and you want to detect an item here. What does it happen if you have an under threshold item here on the optical path of the radar? What happens is that, depending on the area, there is a possibility that this under threshold object attenuates the traveling and coming back waveform from your radar, so that even the item which is above the threshold is simply under the threshold at the end of the elaboration. So just because there is something else in between your optical path, you don't see the thing. Is this written in the standard? No. So again, mission, where I started from, which is the most important thing, defines you the constraints where you have to use this kind of items. You cannot say, I follow the standard, my system is safe, simply because you have placed the right numbers. You have to understand what you're using. Okay, that's the most important thing, which is obvious, but sometimes is not, because people in the companies usually want to deliver the product in the market. So they say, do we accomplish with the local regulation? Do we accomplish with the standards? Yes, okay, that's fine. So it's safe. No, it's not. Okay. Actually, this is what happens. No, here there was one of these radar, and the train was supposed to stop 1 kilometer far away because there were cars in between the lanes, but simply the operator slowed down the train and the people had to push the cars on the side. But this was a system which was declared SIL4, which is not. You see? Simply because they didn't consider some kind of physics. Okay? And these are the application environments in your car. Autonomous car, there are at least 13 microprocessors, a lot of sensors. The point is that, do you think that just following a standard is enough to tell you that your car is safe? And the answer is no. Process plants, aircraft, medical and biomedical systems, because whenever you want to get an analysis, you don't want to get hurt by the system by itself, no? So you want that to be safe. Okay, thank you for the attention. That's over. Okay.
Okay, thank you very much. We have time for questions.
It's not really a question, or maybe you can say something on this, because at the beginning of your presentation you dismissed software as a separate subject, which I agree. There is a couple of differences between software and hardware. One of them that I see is that software doesn't age the same way. So you cannot exhibit failures of software under stressful use. It will just keep behaving the same. So that's one. And the other thing is that failures in hardware are unit failures. I mean, one unit fails, the rest of them works. If there is a failure in software, it's likely that it will just propagate, and every single instance of that software, which you multiply, fails. So how all this theory sort of applies in these conditions where you don't have this duality? I mean, it's just total inverse.
So the question is, software and hardware behaves differently, and so is there any possibility to use this kind of approach in a general way or not? That's the question. Okay. So the answer is, of course it's not possible, because there are parts of the same standard. Consider, for example, safety standard. Safety standard has one part dealing with software, with different tools, different approach, and one part is dealing with the hardware. Concerning the propagation of items, it depends on the system. Consider, for example, a car, no? And if the braking system is not working, it's not just the braking system that is not working. You are traveling, maybe you are taking some holds and you are braking the gears, you are braking some other stuff. It's not a direct propagation, but you may have propagation. That's the reason why there is usually, after an accident, the root cause analysis, because you see a mass of things happening and you have to understand which is the piece that failed first, which is not easy. In terms of general approach, the guidelines are almost the same. That is, there are differences because in the mechanical part and the electronic part, the most challenging thing is to understand how much is my failure rate. That is, how can I model my failure function. In software is, oh my God, what I have to do to be sure that everything is working. I have 10,000 variables. Shall I test all of them for all the possible combination? That may be a problem, but that's the dual part. For each of them, there is a different approach. Of course, you cannot move exactly this kind of way to work from hardware to software, and that's what I said since the beginning. There are two parts. I'm going to deal just with the hardware, not with the software, because of course these are really different things. For sure, what happens is that sometimes one of the difficulties is that in hardware you cannot have masked failures. That is, if there is a failure, it's evident at a certain moment. In software, what happens is that you can have fading transition. For example, think to gamma radiation. You can have in a memory that is in the space a transition from 0 to 1, but when it comes back to the Earth, everything is working perfectly. So simply you have seen something glitching, but that was connected to the mission, not to the fact that the hardware had a permanent failure. So the same thing happens in software. You can have a 1 which becomes a 0, and then it becomes, because there is another mistake, a 1. So this is masked failure. You don't see that, but there is a failure inside. So sometimes in terms of detecting the failure for hardware, usually it's more evident than for software. But the approach should be similar, but it's not the same, cannot be the same due to the complexity. I hope I answer your question.
I mean, we can discuss this for like 2 weeks, I think. So.
I have a question. You said it was preferable to have a hazard function that is analytic. Why is that better than an appropriately smoothed empirical function? What is it that the model gives you?
Yes, because whenever you have the empirical function, you have also to have confidence bounds. And usually these are not provided. So empirical function, you don't know how, usually that you get the function, but you don't know the sample size, you don't know sharply the testing condition, and so the question was why I cannot have, what's the difference from having a an analytical description and an empirical item is why it's not better. The point is that if you have the analytical description, it means that it has been accepted from the user of this item. Otherwise, someone has raised his hand. The empirical one, usually you have to rely on the source to know who has provided this kind of data. Otherwise, they may be not reliable, because at the end of the story, you get a model, and if the one who has performed the experiments has placed garbage in, you get garbage out, even if the model is perfect. So you don't know how the data have been treated, if they are exactly in the same conditions that you are.
Okay, that would be my follow-up question. In an empirical model, you do get the statistics. You don't just get the average, you can get the moments. But you're saying that the problem is knowing whether you can rely on those statistics.
Exactly.
Okay.
The point is that the answer is, are reliability data reliable, that is, can be used? The answer is you have to really pay attention to the data you are placing in your simulator, in your model, because to get information that is valuable for your study, you have to be sure that the information of your items are really close to the mission that you are going to analyze. That is, they get the data that have been taken to implement this hazard function have been taken in similar condition than that you are going to experiment in yours. Otherwise, it may be something that is really different.
Okay. And then a different matter, you had on your slide with the level crossing detectors, there was a thing that none of them are level 4 certified. I was just intrigued by that. Why is that? Is it they're just intrinsically unreliable, the electronics, or?
No, because of the physics. Simply, nowadays it doesn't exist any kind of radar system that is certified. I mean, it exists because I've participated in this study, but in 2017, none of radar system was certified as SAL4 for railway application in Europe. There is something here in Sweden, or I don't remember if in Finland, I don't remember, it's in one of the Scandinavian countries that is certified as SAL3, relying on radar. And the point is that the configuration of the level crossing system are so different that you cannot get the generalized product working for all the possible conditions. Okay. That's the point.
Okay. If there are no other questions, well, thank you again.
Thank you for inviting me here. It has been a pleasure to be here, and I'm really happy, and I would like to thank you and thank Professor Walid Taha for inviting me here in this really nice university.
It was lovely to have you. Roland has a present for you to say thank you.
Thank you very much.
This is a tradition from the university, a gift to carry on.
Okay.
Yeah.
Thank you very
Nice
much.
to have you here.
And thank you very much. Thank you very much. Thank you to the university and to the dean and to all of you for being here, spending your time with me.